We are going to discuss some definite integral using the properties. Integration from 0 pi by 2 natural log of sin f x dx, which is equal to this integral, and this integral is equal to minus pi by 2 natural log of 2. Taking the first integral from 0 to pi by 2 natural log of sin x using the property in which we have said that replacing the variable x by pi by 2 minus x. Evaluating this trigonometric formula, which is equal to cos of x. Now adding these both integral, we get 2I and a summation from 0 to pi by 2 natural log sin of x dx plus 0 to pi by 2 natural log of cos of x dx. Taking integral common, natural log of sin is natural log of cos of x. Sum of natural log is equal to product of the two functions. Again, we convert this sin of x cos of x product to a single trigonometric ratio, divided and multiplied by 2. 2 sin x cos x is equal to sin 2x, and this is 2. Now applying the log formula, in which we have said this formula is natural log of sin 2x, and this is minus natural log of 2, and applying the integral. Now this is constant taking out, and this is natural log of sin 2x. Using substitution, 2x is equal to y. When x is equal to 0, y is equal to 0. When x is equal to 5 by 2, y is equal to 5, putting here. And this is constant, which is equal to natural log of 2x 0 to 5 by 2. Here natural log of sin pi y 1 over 2 dy, 1 over 2 taking out common, 0 to 5 natural log of sin y dy minus pi by 2 natural log of 2. Multiplying this integral by 2 and dividing the upper limit by 2. This 2 will cancel with this 2, and this is natural log of sin y dy minus pi by 2 natural log of 2. This is equal to 0 to 5 by 2 and natural log of sin y dy minus pi by 2 natural log of 2. Now we have studied already in first property of definite integral that this is equal to the same variable function I integral. So taking I on the left side, subtracting 2I minus I and minus pi by 2 natural log of 2, which is the required answer. Now we are going to discuss another example 3. 0 to 5 by 2 sin of x plus cos of x dx, which is equal to this integral, and this is equal to 5 by 4. Taking the first integral and using the property replacing x here and here by pi by 2 minus x. Expanding these formulae, we get this is cos x, this is cos x, and this is sin x. Again adding 1 and 2, we get 2I, and adding these two integral, since the denominator of both integral are same, taking LCM and adding the numerator, both are same, cancelling, we get 0 to 5 by 2 1 dx. Integrating this x 0 to 5 by 2, which is equal to 2I is equal to 5 by 2 minus 0, dividing by 2, we get the required answer. Again, another interesting example, prove that integration from 0 to pi by 2 natural log of tangent x dx is equal to 0. Now we know that 0 to pi by 2 natural log of tangent x dx we can write as 0 to 5 by 2 natural log sin of x divided by cos of x dx. This is a quotient. When we apply log, it can be written in difference form as. Again, we apply integration to these both. This is because integration is linear, to apply to the first function minus second function. Now using the property in the second integral, natural log cos a pi by 2 minus is evaluating this is equal to 0 to pi by 2 natural log of sin is cancelling, and we get the required answer, which is 0. Here is another example. This example at page 343, and this is example 5 in the book. Integration from 0 1 arc tangent 2x minus 1 1 plus x minus x square dx. If we evaluate this integral by direct method, this is very difficult. If we use the property, then this is a simple case. Replacing x by upper limit minus x formula, this can be written as tangent inverse 2x minus 1 1 plus x minus x square dx. Replacing x by 1 minus x here, and here, we get simplifying 2 minus 2x minus 1 1 plus 1 minus x minus expanding this formula and multiplying by minus 1 minus x square plus 2x, cancelling 1 with minus 1 and simplifying, we get this. Taking minus common, since tangent inverse is odd function, we can take out minus outside. So tangent inverse 2x minus 1 1 plus x square minus x square, which is again I but minus I, bringing on left hand side and adding 2I is equal to 0, and that is I is equal to 0. Now we are going to discuss some integral conversion and diversion. Some definition, these are important. This is for exercise 7.4. A definite integral from a to b of x dx is called improper if it has one or more point of discontinuity over closed interval ab, or it has one limit of integration is infinity. For improper integral are called generalized or infinite integrals. Here are some cases, various cases. First case, integration from a to infinity f of x dx. This can be written as limit capital M tends to infinity a to m f of x dx. If this integral exists, then we said that this integral is convergent. If the value of this integral is infinite, then we say that this integral is diverges. Similarly, from minus infinity to b f of x dx, it can be written as limit small m tends to minus infinity m to b f of x dx. If this integral exists, we say that this integral converges, otherwise it is divergent. If there exists c belong to ab, at which f of x become infinite or discontinuous, then the integration from a to b f of x dx in this case is defined as integration from a to b f of x dx, splitting at c from a to c f of x dx plus 3c to b f of x dx, provided that both sides of the integral on the right hand side converges. Such properties can be used to solve exercise 7.4 for conversion or divergent integral. Thank you.